This is Unit 10, Lesson 10, Graphing Logarithmic and Exponential Equations. In this section, we're going to talk about what logarithmic and exponential equations look like and the transformations on their graphs. The transformations are going to be very similar to what we did with transformations of all the different other types of equations that we've done, like quadratics, square root functions, and things like that. So the first thing you need to realize is that exponential equations are of the form y equals ab to the x, and that the a value there is the y-intercept, and that's not going to change for exponential equations that are graphed. If I wanted to graph the equation y equals 2 to the x, the y-intercept here, understand that this is understood to be y equals a times b to the x. So the number that's understood to be in front of that 2 is a 1. So we could say that this equation is the same as the equation y equals 1 times 2 to the x. Our b value is 2, our a value is 1. So what this tells us is that the graph of this equation is going to cross the y-axis at the a value, which is 1. So we're going to look at this graph in Desmos. And it's really important that you understand how to identify the parent function of this as well. So I'm going to go into Desmos and we're going to look at this parent function. If I type in y equals 2 to the x, that graph looks like this. And I'm going to change the graph so that it's a one-to-one graph so we can see exactly what's happening here. And you can see that the y-intercept is at 0, 1. And exponential equations, when somebody says something increases exponentially, this is what they're talking about. This graph gets very big very quickly. In other words, as we plug in larger and larger x values, this graph gets big very fast. So if this is the equation, y equals 2 to the x, then if I had y equals 2 to the first, if x is 1, we would plug 1 in for the x and get 2. If I plug 2 in for the x, y equals 2 to the second, we would get 4. And you can see every time I plug in a new number, this graph is getting exponentially large. If I plug 5 in, I would be up to 2 to the fifth, which is 32. So it gets very large very quickly. It's also very important to understand what the parent graph in an exponential function is, and I'm just going to explain that to you real quick. Here I've got 4 different exponential equations. The one that we've been talking about is y equals 2 to the x. Now, I can do transformations on that graph by adding or subtracting something to the x part and then adding or subtracting something to the whole thing on the outside. So this would be considered the inside, this would be considered the outside. And when I have y equals 2 to a power, whether there's something added to that or added on the outside, doesn't matter. The y equals 2 to the x would be considered my parent graph. So here, something like this, y equals 3 to the x is my parent graph. Y equals 5 to the x could be a parent graph. So what if I have something like this? What do you think my parent graph would be in this case? Well, I would say my parent graph will be y equals 6 to the x. Whatever this whole number is to the power of x is going to be my parent function. So that's how we identify parent functions of exponential equations. So we've graphed the y equals 2 to the x equation in Desmos. And so now I'm going to take some different variations of this graph and graph them in Desmos as well so that you can see how the parent graph is affected by the transformations. And so let's just think about this in terms of the inside and the outside. The inside part of the graph is going to be what is here with the x value. It will usually be in parentheses if something is added to that exponent, and that would be considered the inside part. So if you think back to when we did quadratics, if we added or subtracted something to the inside, we said what was added or subtracted to the inside will change it to the right or left. It'll move it right or left, the opposite of what we would think. So if it's added on the inside, it moves left. If it's subtracted on the inside, it would move right. So for this one, that y equals 2 to the x graph, since this plus 1 is on the inside of parentheses, I'm going to think about that transformation as it moving to the left 1 unit. For this one, since the plus 3 is on the outside of the exponent, that plus 3 on the outside, remember, moved up or down depending on whether this was plus or minus. If it was a plus, it moves up. If it was a minus, it moves down. So I'm going to say that this one from the parent graph y equals 2 to the x is moving up 3 units. So here I've got a graph of those 3 graphs put on the same coordinate system. The y equals 2 to the x graph is the one in black here. That was the original graph. And you can see the a value was 1. That's where it crosses the y-axis. And I'm going to use that point as a reference for what's happening with these other two. So if you look at this point where in the original or in the parent function it crosses the y-axis, this green function is a transformation, and I'm going to say, okay, this is an x plus 3. So I'm going to say, well, that graph is going to move left 3 because it's an inside transformation. The inside tells us right or left. And so if you look at this y-intercept and how it affects the original graph, this black graph is the original, remember. If I take this ordered pair, it is in fact moving 3 units to the left. And if we look at all of these different points, this point at 1, 2 moves 3 units to the left. 2, 4 moves 3 units to the left. And we can see that that happens from the black graph to the green graph. That happens in every single place. For the y equals 2 to the x plus 3, we said that that plus 3 is probably going to make our parent graph move up 3. And that's in fact what it does. This graph moves up 3 from its original position. This ordered pair up 3. This ordered pair up 3. So you can see how transformations work in this exponential equation. So we can look at a bunch of different similar graphs to see what is happening here. And this is just another look at in this one, the orange function is the y equals 2 to the x, the original graph. 2 to the x plus 3 moves up 3. That's the same graph as before. 2 to the x minus 3, notice it's moving down 3 units. Every single spot has moved down 3 units, and you can see that happening. So if you look at this transformation, now this one doesn't show us the original graph. If the parent function here was y equals 2 to the x, which it would be, looking at this function, we would expect that y equals 2 to the x graph to have transformed left 1 and down 3. And if you think about what the original graph would have looked like, it would have crossed the y-axis here. The point 1, 2 would be on that graph. The point 2, 4 would have been on that graph. And you can see in blue, I've drawn a real simple y equals 2 to the x graph, and let's see if in fact that does happen. We were expecting this graph to move left 1 and down 3. So if this graph would move left 1 and down 3. So there's that point. This point, left 1 and down 3. You can see where that is. This point, left 1 and down 3. You can see that that's about right there. So we can see that the transformation that we thought would happen is in fact happening. So now I want to consider what happens if we've got the parent graph here is y equals 2 to the x still, but we've instead of having a 1 in front, we have a 3 in front. Look at what happens to the graph. Instead of having the y equals 2 to the x cross the y-axis at 1, look where it's crossing. It's crossing at 3. And we can see that it changes that graph a bit. That's something called a vertical stretch. You will learn more about that in pre-cal. It stretches the graph. Putting that number in front stretches the graph and makes it look a little bit different. And you'll explore more of those in pre-calculus next year. Vertical compression is when we put a fraction in front of the graph. And we talked about putting whole numbers and fractions in front of parabolas earlier in the year. Those were vertical stretches and vertical compressions as well. But how they affect the different graphs is different based on the type of graph that it is. So this one is just a quick glance at what a vertical compression is when you put a fraction in front. So this one, the original parent function was f of x equals 2 to the x. The vertical compression is what happens when we put a fraction in front. So the h of x equals 1/3 times 2 to the x. The 1/3 now becomes your y-intercept, or your a value. Here we're exploring what happens to our y equals 2 to the x line when we put a negative in front. And putting a negative in front is going to make it reflect across the x-axis. So instead of my a value being at 1, my a value is now going to be at -1. So this transformation is what happens when we put a -1 in front of the y equals 2 to the x. So we have a -1 in front that flips it across the x-axis. And our y-intercept now becomes a -1, because this number is always going to be our y-intercept in an exponential equation. Here, we've got f of x equals 2 to the x, and we're talking about what happens when we multiply the exponent by a negative. Well, that will flip it across the y-axis. Now, all of these things can be graphed in Desmos. It's not important that we know how to graph them by hand, but we should be able to recognize the type of different things, the type of transformations that are going to take place when we do these mathematical operations to the parent function graph. We're going to now talk about how exponential equations and logarithmic equations relate to each other. We need to remember that when we first started studying logarithms, we learned how to convert logs to exponentials and exponentials back to logs. We learned how to go back and forth. Well, that is needed to be able to determine what the graph of a logarithmic equation looks like. And so if you remember that the exponential functions can be converted into logarithmic functions, what would the inverse of that function to the left look like? Well, if we're thinking about the inverse of that in terms of just the graph, so we're going to draw this, the inverse of this function, and then we're going to talk about how that relates to a logarithmic equation. We know that the graph of inverses have ordered pairs that have been switched. In other words, if I take a few of these ordered pairs that are on this graph, and I'm just going to take this one right here, the 0, 1, and I'm going to take this one, 1, 3. Those are the only two real corner points that I have that I can find definitive inverses of. So those are the 2 points that I'm going to use. I'm going to write those down. And if I think about the inverses of these ordered pairs, wouldn't the inverse of those ordered pairs just be those ordered pairs flipped? We switch the x and the y to find the inverses. So the inverse of the ordered pair 0, 1 is 1, 0. And the inverse of the ordered pair 1, 3 is 3, 1. We flip the x and the y coordinates. So I'm going to just take these two inverse ordered pairs and graph them. So 1, 0 is the inverse of 0, 1. And 3, 1 is the inverse of 1, 3. And then notice here, when the exponential equation was being drawn in red here, the exponential equation kind of hugs the x-axis. That's an asymptote, and it goes up infinitely, quickly. So instead of hugging the x-axis like this one did, this one is going to be the inverse. It's going to kind of hug the y-axis, get closer and closer and closer to the y-axis. So if we think about what this graph would look like if I draw it, it's going to look something like this. Now, that's certainly not perfect because I drew it by hand and not on a computer, but you can hopefully see that if I take the y equals x line and fold this graph across that y equals x line, these two graphs would lie on top of each other. They are, in fact, inverses of each other. So in order to study this a little bit more, we need to think back to when we found inverses in Unit 8, Lesson 6. We learned how to find inverses, and we learned that if we want to find the inverse of y equals 2x minus 4, we can switch the x and y, and then we would solve for y. So y equals x plus 4 over 2 is considered the inverse of y equals 2x minus 4. And if I were to graph those two things on Desmos, let's look at what happens to those two graphs. So I'm going to graph y equals 2x minus 4, and I'm going to graph y equals 1/2 x plus 2. So going back into Desmos, if I put those two equations in, y equals 2x minus 4 and y equals 1/2 x plus 2, here I can see the two inverse functions. Now, notice, if I were to draw the line y equals x, that is the line of symmetry. If I were to fold this graph across this line, wouldn't these two lines lie on top of each other? That's what makes them inverses. Another thing you could consider here is the ordered pairs. Look at the green line. This ordered pair is 0, 2. So 2, 0 would be on the blue line. This ordered pair is 2, 3. So 3, 2 would be on the blue line. And there it is. This ordered pair, 4, 4, is on both lines. Let's see. This ordered pair right here, negative 10, negative 3, would tell me that negative 3, negative 10 would be on the blue line. And there it is. So you can see that these two, the blue and the green line, are inverses of each other because every single ordered pair on the blue line, if you flip it, is on the green line. That makes them inverses. So here we've got the equation y equals 3 to the x in right here. And this animation is transforming that into its logarithmic form, or the inverse of that equation. So we need to think back to when we were converting exponential equations to logarithmic equations to see how this works. And so if the inverse of an exponential function is a logarithmic function, and we can convert y equals 3 to the x to its logarithmic form of log base 3 of y equals x. Notice the base is 3 here, so the base of the log will be 3. The x is your exponent, so the log will equal the exponent to give us this log base 3 of y equals x. Remember in chapter 8, lesson 3, when we were trying to find the inverse of a function, we switched the x and the y. So if we switch x and y of log base 3 of y equals x, we will end up getting log base 3 of x equals y. And that is the graph that is being graphed right here in this animation. So here in this graph, the black graph is the y equals 3 to the x graph, and the red graph is the y equals log base 3 of x graph. I've graphed those in Desmos so that you can see what they look like. And if you look at the y equals x line, or if this graph was folded across that y equals x line, those two graphs would lie on top of each other. So we have graphed the inverse of an exponential function, which is the logarithmic function. This is the inverse function of the y equals 3 to the x exponential function. This is its inverse function. So what we can take from this is the shape of a log function is going to be, as we move left, it's going to approach the y-axis. Parent function will approach the y-axis, and it will go forever toward the right in a gradual increase. It will decrease toward negative infinity. This is the shape of a basic log function. So if we're trying to graph natural logs, the shape of a natural log function is going to look very similar to this. So this one's an exponential function, gets big exponentially. This is a log function. So here I have three natural log functions. The natural log function, y equals natural log of x, is our parent function here. And we're going to graph these three functions in Desmos. Y equals natural log of x, y equals natural log of x plus 1, and y equals natural log of x with a plus 3 on the outside. So this is our parent function. What would you expect to happen to the parent function using this function? We've got a plus 1 on the inside. Well, plus 1 on the inside tells me that this parent function will move left 1 unit. This plus 3 on the outside tells me that this parent function is going to move up 3 units. So looking at this slide, let's consider what the y equals natural log of x function looks like, and that's it in blue. And it says the graph to the left is the parent function of the y equals natural log of x equation, and transformations for the natural log function are going to work the same way. In this slide, I have the same three natural log equations that I had in the slide before, and we're going to be able to see the transformations of this black parent function, y equals natural log of x. With the natural log of x plus 1 and the x plus 1 is on the inside, hopefully you can see that every one of these corner points is moving to the left 1 unit. Going from the black function to the green function, we said here that the plus 3 would tell us this function moves up 3. And you can see that very distinctly right here. That point moves up 3 units. this point moves up 3 units. So the transformations work the same way for the natural log function as they do for all the other functions that we've studied. Hopefully you remember when we talked about exponential functions and natural log functions, we talked about how those two functions were inverses of each other, and if I want to eliminate a natural log function, I would put an e in front, and if I want to eliminate an e function, I put a natural log in front, making those functions inverses. And you can see here, this is your e to the x function, this is your natural log of x function, with the y equals x line graphed in between. And if we fold that graph along that y equals x line, you can see that those two would be inverses. They would lie on top of each other. Okay, so let's just consider a random graph. Y equals 3 to the x is my parent function. What do you think would happen with this function if I were to graph it on the same coordinate system as the y equals 3 to the x line? I'm going to say that it would move right 5 and it would move up 2 because of the transformation. And the good thing about this is you don't have to do these by hand. You can graph them in Desmos, you can predict what you think would happen, then graph the second function in Desmos and see if what you predicted is true. There is nothing that says you have to be able to draw these by hand. Desmos is fine. If you have to take the SOL, you can use Desmos for the entire test. So it's good to understand basic shifts and basic transformations, basically what happens with these. But when it's all said and done, don't panic about this and don't try to graph them by hand. Desmos does all the work for you. So here are those two functions graphed. The y equals 3 to the x is the black graph, my parent function, and then you can just look at different ordered pairs. The 1 was the y-intercept. I predicted that I was going to go right 5 and up 2. 1, 2, 3, 4, 5, 1, 2. And in fact, that is what's happening with this graph. We go right 5, up 2 to get to all the other corner points. This kind of hugged the x-axis. Now this graph is going to kind of hug the 2. So we could say in the parent function, the x-axis is an asymptote, a horizontal asymptote. We can say in the transformation function, y equals 2 is the asymptote. And that's usually what they're going to ask on the SOL. What is the asymptote line of the exponential function or the logarithmic function, whatever it may be? If my original equation was y equals 5 to the x, that's my parent function. My parent function is here in black. And you can predict the green graph from the parent function, y equals 5 to the x. The green graph is going to go left 4, down 3. So here's my parent function. It goes left 4, down 3. And you can see that in fact that is what's happening here. For the purple function, I would predict that it's going right 1, up 4. So I'm going right 1, up 4, and yes, that is what's happening with the purple graph. So there's a lot you can do without even graphing these. You can predict where these things are going to be. For this green graph, the asymptote is at y equals -3. It's kind of hugging that y equals -3 line. For the purple graph, the asymptote is y equals 4. It's getting closer and closer and closer to the y equals 4 line. So basically in today's assignment, all you're going to have to do is predict what's happening with the transformations, whether it's moving right or left and how many, and whether it's moving up or down and how many. It's very simple. We just need basic understandings of the transformations.